Lovely. So we'll still give it a few more minutes, I guess, to get everyone to log on entirely. Okay. So I guess maybe we can start right now. So if I may, my name is Wolfgang Ungra. I'm a member of the board of the MIT Club of Germany. It's a great pleasure to welcome all of those who found their way to this event to join in from possibly different parts of the world. That wouldn't be surprising. We are hosting this year's fourth event. And this is a completely new event for us. It's a workshop event, but it's still consistent in our series called Climate Change Matters. And it's a great privilege today to have somebody as knowledgeable and as active as Tamara joining in and taking us through this workshop. So I will get to her in a few minutes. Maybe for those who are not aware of the MIT Club of Germany or not yet so aware, we would like to say a couple of things on the MIT Club of Germany. For that, I would like to hand over to Helmut, who's our president, to just give us a little insight again in what we do here in Germany for those, again, who aren't aware of us. And I will share my screen to do just that. So bear with me, check, as we just quickly go over a few slides and then we'll hand over and get straight into the workshop. So over to you, Helmut.
Yeah, thanks a lot, Wolfgang. Yeah, my name is Helmut Lotze. I'm the president of the MIT Club of Germany. The MIT Club of Germany is actually the alumni organization of all alumni within Germany. We are consisting at the moment of about 200 members, and the alumni crowd is about 500 alumni in Germany. What we normally do, we have actually a couple of major events in a year. One is the annual general meeting, which is held normally in spring, but this year, because of the specific situation, we will hold this in September. Then we have another large event, which is actually a series of, is called Schule mit Wissenschaft, or in English, school with science. This is consists also of a couple of event modules, presentations, workshops, and social interaction. And then we have a third strategy, third line. This is actually what we are doing right now, events and workshops to topics such as climate, renewable energy, and so on. Okay, so again, I welcome everybody, and I hand over to Wolfgang again.
Thank you. Thanks, Helmut. So as Helmut was alluding to, we set up this climate change series because we believe there's probably hardly a bigger topic, despite Corona, which has kept us all busy in our toes. In fact, even creating this format of an online event, which was new to us, but we started it last fall as a result of Corona. And we have in this series, because we we're very serious about it, about these topics, and we would love to move it beyond just events to actual actions, and involving also other players, but we are just building up this network right now. We have different formats. We have expert panels, so anyone who's already joined us before, you might know that we had expert panels, and we had a fireside chat. And today is a new format, which is the workshop. And again, as always, it all has to do with looking at climate change from different perspectives, understanding tools and things that we can do. Now, needless to say, we don't want this to just be a one-on-one or a one-to-many event, but we would like to have a good amount of interaction. So there is the Q&A box. We would love to ask you in the main session, and in particular to ask questions. And maybe this is more relevant once we come out of the workshops or the breakout rooms and have everyone in the main forum again. So you might want to ask various questions to make it more interactive. And of course, we will try to answer the questions in the time that we have. We have about 1.5 hours reserved for this event. Sometimes it is difficult to get through all the questions, so we would then take them back and see how we can answer them afterwards. Today's event lines into a series of discussions we've had on supply chains, on policies. We will be looking at, in particular, the model, which is called EnRoads. I don't know, Peter Senge introduced it, and he pointed us to it, which was great at the time. But of course, it's very complex. There's a lot behind it, and trying to understand a bit more how to actually deal with it is today's idea. And why is that so important? Because the task at hand is just so immensely complex. There are so many interdependent parts in every country, but also, of course, on a global basis. Things are coupled, tightly coupled. And the unfortunate thing, which we are hearing almost on a daily basis from studies coming out, is that those action is required at such an imminent time, which doesn't allow us to actually try out a lot for the next 10 years. I think right now everyone is looking at what are the solutions that we can implement. And it has to be small solutions, but it also has to be a bigger governance. And so for us, today's workshop is going to be looking at understanding this complex system and how to organize them. And the EnRoads model is one way, one instrument to manage complexity. I feel encouraged also from Tamra's website, knowing that actually this is something that you find is very applicable, not only to governments and businesses, but also to schools, colleges, universities, different institutions that can work with this. So I think the relevance of this model is very high. And I think it is great that you're able to share your insights, your understanding, and try to inspire people to look at that as a way of getting through complexity, because you have such a broad background. You studied astronomy, meteorology. You've been engaged you did your PhD at MIT in 1983, which of course prepared you for also in meteorology for understanding complex systems. You're very engaged right now in STEM subjects. You are right now actually working amongst others as an education consultant on earth and climate issues. You are at Bentley University as an adjunct professor, and so you're also teaching, I guess, and doing your research. You worked at, until 2017, a Harvard Advanced Leadership Initiative fellow, where you also explored numerous issues around climate change. So frankly, you have in-depth knowledge from your education. You are active in many ways. You've obviously chosen to adopt this model for good reasons. You're engaged in the MIT community. That's why you're here today. And it's a great honor to welcome you and to understand more why you feel that the EnRoads model has worked well for you and is valuable, and of course also to make us more acquainted with it and take us into how we can apply it to our own areas that we all work in and get engaged in. So without further ado, I would like to actually hand over to you and ask you to kindly take over and take us through it. We're very keen and we're very much looking forward to understanding more. So over to you, Tamara.
Okay, well, thank you very much, Helmut and Wolf, for having me here to share the EnRoads model with you. I will say, just to build up a little, thank you for that very kind introduction. I have been using the EnRoads model for, it's actually going, it's over a year now. I do teach global climate change at Bentley University, which is a business school. So a lot of the work that I do is to help people who are not going to be in STEM careers, but need to understand climate change in the context of the decisions that they will make in their careers. Learn a little bit more about climate change and understand when they need expertise in the sciences to make those effective decisions. I will also say that I have used the EnRoads model for this past year, and through the support of the MIT Alumni for Climate Action Group, which I've been a part of for a year, and we have one of our members, Tim Connors, has joined us today. He leads the education and mobilization part of that group. And one of our goals was to reach over 1,000 people in the first year. April was about a year out. We reached over 1,000 people. And these were other MIT alumni groups. I work with teachers so that teachers can bring this model to their students. I've run it with student groups and with all other and with lots of other kinds of mixed groups in terms of age level. So it's a very powerful model. It has been used with legislators in the United States and around the world, and we'll see that in a few minutes. Here is how widely this has been used to help people understand which are the high-level solutions that you might implement to address the climate issue. So EnRoads stands for Energy, Rapid Overview, and Decision Support Model. It was developed by Climate Interactive, a nonprofit in the United States in association with MIT's Sustainability Initiative. So this is what we're going to do today. We're going to have a brief overview of the science of climate, and then we're going to start exploring the model. This will be interactive. I will have you make suggestions of solutions that we're going to test out of the model in the chat. So we won't have that Q&A box, but we do have the chat, and I will be wanting to use the chat to provide suggested solutions. And so we will communicate that way. And then we'll have a debrief at the end. So let's briefly review the science of what's at stake. So this is a graph showing the carbon dioxide levels over the past 800,000 years. And just to get oriented here is the time scale. Time does go from left to right, with the present being defined as 1950 right here, and going back 800,000 years. And as you can see, the amount of carbon dioxide in the atmosphere has dramatically varied over that period of time. But it has varied between a low of about 170 parts per million. Here is the vertical scale here of carbon dioxide concentration in parts per million, going from 160 to 480 here. So the low is about 675,000 years ago at about 170 parts per million. And the high during this period is about 325,000 years ago, where it approaches 300 parts per million. And it exceeded 300 parts per million around 1950. On this scale, the line goes straight up after that, where the current levels are about 420 parts per million. So where did all this carbon dioxide come from? So this graph is, the time scale has changed a bit. Now this goes from 1850 to 2018. And then this is the emissions, the vertical scale is the emissions of carbon dioxide in gigatons of carbon dioxide per year. As you can see, back in 1850, really most of that input of emissions of carbon dioxide came from land use changes. That was like the clearing of land to create agricultural lands, the clearing of forests to create agricultural lands. I think you can see in the late 1800s, coal became a significant source of energy and thus emissions of carbon dioxide in the atmosphere. And that has grown over time. And then in the early 1900s, oil became another significant source of energy and thus in emissions of carbon dioxide to the atmosphere, and has also grown over time. After about 1950, natural gas became a significant source of energy and has grown. And the others here are emissions from cement production and gas flaring. Gas flaring is what happens during oil production. Methane, a gas is produced. And a lot of times it can either be just let go into the atmosphere, or it can be burned. And that's what the flaring is. They burn it off. And then here are the land use changes. So you can see all of these have grown over time a bit. Land use changes has gone up and down a bit, but it has not grown significantly like the other sources have. So these are the inputs of gases in the emissions, CO2 emissions into the atmosphere, but those aren't the only emissions of greenhouse gases. In addition to the carbon dioxide from fossil fuels, which makes up a total of 68% of all of the greenhouse gas emissions, and then the CO2 emissions from land use and forestry makes up 7%. The rest of it comes from these other gases: methane, nitrous oxide, and the F gases, or fluorochlorocarbonated gases. You'll notice this scale here, the timeline is the same as the last one, 1850 to close to the present. The greenhouse gas emissions are in gigatons of carbon dioxide equivalents per year, as opposed to just carbon dioxide. So molecule for molecule, for example, methane is like 25 times more powerful molecule for molecule as a greenhouse gas, but it is much smaller quantities in the atmosphere. So what this graph is putting everything on a scale of how powerful it is with respect to carbon dioxide. So you can see that the emissions of greenhouse gas emissions from methane make up 18% of those gas emissions. Nitrous oxide makes up 5%. About 50% of the methane comes from agricultural practices. And about, I think, 60% of the nitrous oxide come from agricultural practices. The rest of those comes from heavy industry and manufacturing. So what impact does this have on temperatures? Well, we're looking here at two global records of temperature change. Again, starting at 1850 and going up past 2010. These here are, the vertical scale is temperature anomalies. What that means is it's how the temperature is changed at any particular time along the scale compared to a standard. In this case, the standard is 1850. So you can see here at 1850, the temperature anomaly is 0, but that every year after that is some difference from 1850. And so you have two records here. The red one is from the Hadley Meteorological Center in the UK, and the yellow one is the Goddard Institute for Space Studies in the United States. And as you can see, while the early parts of the records are made up from different records, and the Hadley Center record goes back a bit further than the United States record, you can see that pretty much the ups and downs pretty much match on these two records till we get to 1970. It was 1970 when we began to have very reliable satellite information. You can see after 1970, these records are pretty much in lockstep, showing an increase in temperatures from 1850 of on the order of 1 degree Celsius and 1.8 degrees Fahrenheit. So, so if we continue this, the type of the amounts of greenhouse gases we are having emitted into the atmosphere, the estimate is that the temperature will increase by 3.6 degrees Celsius or 6.5 degrees Fahrenheit by the year 2100. So this graph, and this is the scale that we will be using in the EnRoads model, goes from the year 2000 to 2100. And we're here now at about 2021. We have two scales on here right now. The baseline is basically following what the world is doing now in terms of increasing emissions over time. Since we haven't implemented any solutions, the current scenario matches that. But the Paris Agreement has set the goal for the world to not exceed an increase in temperatures of any more than 2 degrees C by the year 2100, and to strive for only 1.5 degrees C by the year 2100. So the goal that we will have is to try to get this temperature down to here. But what would an increase of 3.6 degrees Celsius actually mean for the world? And so these are just some of the examples. Arctic sea ice would be gone 2 out of every 3 summers. This has never happened in history, even in geologic history, unless you go back really past the moving of the continents. Arctic sea ice has been decreasing in the summertime, but the minimum that it's been has been like 2/3 of the Arctic Ocean is covered with sea ice in September, and that happened in 2012. But that's getting smaller and smaller. So it's predicted that with an increase of more than 3 degrees C, 2 out of every 3 summers would be ice-free in the Arctic. In addition, 50% of insect species would lose over 50% of their habitat range. This has really serious implications for agriculture as we depend on these insect species to pollinate our crops. We've heard a lot about droughts in various parts of the world. The droughts would be on average 11 months longer than they are now. And burn areas by summer wildfires, and this one says in the Mediterranean, would double compared to today. And so we already know that we've heard about wildfires in Australia and in the western part of the United States. The areas of burn are becoming pretty significant, and the length of time of the wildfire season has also increased tremendously. Another aspect of the impacts of climate change is a rising sea level. So this is just a tool that you could use, and I have some examples here. Here is the URL for the tool, so you can put in other cities. I put here Boston, this is where I live, and this is Boston today, so the global rise in temperature right now is set to 0 compared to today. And so here is the land area in Boston. And now if we watch the slider, I'm just going to go up to the next graph. We're going to move the slider up to 3.5 degrees C. And so you can see this is the area of Boston, again, this is where I live, is a significant part of Boston is underwater. And here, if you've ever flown into Boston, this is the airport. So it would be completely underwater. And then I chose a city in Europe. Here is Amsterdam today. And if we now increase the temperature, the global temperature by 3.5 degrees, this is Amsterdam with an increase of 3.5 degrees. So you can see all of this area would be underwater. And this is a sea level rise of 26 feet or 7.9 meters. The other example I have is New York City today. So this is Manhattan. This is New Jersey Shore, the state of New Jersey Shore, and this is Brooklyn and Queens as part of New York. And I'll call your attention down here to the tip of Manhattan. This is where Wall Street is, and that has relevance for a couple slides from now. And this is New York City with a 3.5 increase in temperature. You can see all of the New Jersey Shore is pretty much underwater. A good fraction of Queens and Brooklyn, New York are underwater, and significant fractions of Manhattan are underwater. And again, here is where Wall Street is. Now let's go on the ground in Wall Street. This is Wall Street today. People are coming back, and I'll call your attention to these 2 women who are walking by this window of this building. You see their heads are about the level of halfway up the building. If we have a 4 degrees C of warming in New York, this is what the Manhattan would look like. And you can see that the water level here is about 3/4 of the way up those windows. So all of those people would be underwater. A few other cities on the ground. This is London with 4 degrees of warming. This is Parliament, and you can see the entire lower level of Parliament is underwater. This is the Thames River and the Westminster Bridge, and the ends of the Westminster Bridge are underwater. So climate-related disasters cost the world $650 billion just between 2016 and 2018. But the damages the IPCC has associated with global warming could total over $54 trillion by the time we reach just 1.5 degrees C. So now we're going to explore how can we address this issue. And so for that, we're going to use this EnRoads model. So here is the a screenshot of the EnRoads model. And we'll be looking at this in more detail. Here is the URL. You could actually go to it yourself, and I'm hoping you will at some point. I will actually share the URL with you. But here we have the global, just to orient you to the framework. Here's the global sources of primary energy. Coal is this brown wedge here. Oil is the red wedge, and you're going from the year 2000 to 2100. The vertical axis is exajoules per year, so an amount of energy per year, and you can see that this is increasing over time. We have natural gas, renewable energies, bioenergy, nuclear energy, it's a little blue up here, and new zero. New zero carbon is basically a new technology that we have not discovered yet, but will discover between now and the year 2100. Which is relatively cheap energy with zero carbon emissions. So that's another potential source of energy. Here we have the greenhouse gas net emissions, and since again we have not implemented any solutions, the baseline and the current scenario are the same. We have here the various kind of solutions we can implement. The energy supply includes coal, oil, natural gas, bioenergy, renewable energy, nuclear energy, that's new zero carbon, and implementing a carbon price and how that might impact the emissions of greenhouse gases. Then we have here for transportation and for buildings and industry, we can increase the energy efficiency of each of those. And we can also transition them to electrification from their fossil fuel sources of energy now. Another lever that we can pull is growth. One is the population growth, and it's not saying the population should go down, but potentially slowing the growth from its current rate, or economic growth. Over here we have land and industry emissions. So here we have methane and other gases. So these are those other gases besides carbon dioxide that are powerful greenhouse gases. We have reducing deforestation. Forests are a natural capture of greenhouse gases. So if you have deforestation, that increases emissions. And then carbon removal, both afforestation, the planting of new trees, and technological carbon removal. Before we get into the looking at the model itself, I want to give you a sense of, since this is an MIT alumni group, of how we can trust this model. So EnRoads is a very complex model, but it doesn't have the actual physics of the climate systems or the social science calculations for the economics of the system. So other more complex and disaggregated models are used to give decision makers information about the possible futures with higher degrees of spatial resolution and more details on the impacts of and economic considerations that need to come into making decisions with respect to climate. But the EnRoads is a simple model that allows you to, and it mimics what those more complex models do. So it complements them and allows users to gain insights into what these more complex models are. So there is a give and take between these two kinds of models. These complex disaggregated models take a lot of time to run and incorporate a lot of physics and economic models. then they can then inform the development of roads, of models like EnRoads. C-Roads is another climate interactive product. It's called Climate Rapid Overview and Decision Support Model. And it is used in the context of simulating an international negotiation around climate change that would produce an agreement similar to the Paris Agreement. So how do we test the EnRoads model against these other models? Well, we look at the extreme conditions. Can the simulation, is the simulation robust to combinations of high and low policy inputs when we make those changes in the EnRoads model? Are the assumptions to is the sensitivity assumptions important? Like, when you change those parameters, do those insights change? And I'll show you exactly where you can change those sensitivity assumptions. And then can you reproduce historical behavior of the climate systems? So how do the outputs compare? And this is just some examples of how EnRoads has compared both historically. Here are the, this is the history. So it goes from 1990 to 2015. These are the more complex integrated models results, and this is EnRoads. So the answers aren't exactly the same, but it gives you, in terms of exajoules per year, the amount of energy per year, you're in the right ballpark, and the sense of the changes are accurate. And these are the forecasts out into the future, comparing the EnRoads model to all of those more complex models. And you can see that they fit within the scope of these other models. So that's just a brief overview of how we know that the model is accurate, or it is useful. And this just gives you a sense of the implementations of EnRoads around the world. The model itself was released to the public in December of 2019. And since then, they have had almost 2,500 events with almost 63,000 participants, covering North America, South America, Europe, Africa, and Asia, Australia. They actually run a program called the EnRoads Climate Ambassador Program, in which they basically train people like me to run these kinds of workshops. And they have ambassadors all over the world. Okay, so now let's actually go to the model. What I am going to do is I'm going to give you the link to this, the dashboard. So let me I'm going to put this link in the chat so that you have access to these documents, and I will explain what they are. Let me find the chat here. Oh, there it is, chat. Okay, so there are four documents here. The main ones to look at is the first one, the EnRoads one-page guide to control panel, and I'll be showing these on the slides in a second, and the multi-solving co-benefits and equity considerations of using these models. So here is the model itself. I got to go back to the slides though. There we go. So this is, there we go. This is the EnRoads control panel. That's the first document in that Google folder that I just gave you the link for. If you'll notice, the center section here is exactly all those different solutions that were in the bottom of that scenario, the slide that I showed you. And this each one of these bubbles gives you a sense of what pulling this lever means. So for example, for coal, if you pull this lever, you'll be highly taxing coal. And what does that mean? It means you're discouraged. Well, you can also go this way and subsidize coal. So you're taxing or subsidizing coal. So either you're discouraging or encouraging the mining of coal and the burning of it in power plants. If we look at new zero carbon, that's this one here. If you pull this lever, you're discovering a brand new cheap source of electricity that does not emit greenhouse gases. If we go to technological carbon removal, this one is the technological pulling of carbon dioxide out of the air with these new technologies that enhance natural removal, such as afforestation, or manually sequestering and storing carbon. So this is just to give you an idea of what the different solutions mean in terms of implementing them. We also want to consider consider the solutions in a multi-solving, through a multi-solving lens. A lot of the solutions, most of the solutions that were on that last slide are long-term in scope. You need to start implementing them right away, but the significant impacts are not going to come until 10, 20, 30, 40 years. And so we want to also look at those short-term co-benefits. What are the co-benefits of these solutions, and what are the equity considerations of these solutions? So this is a Climate Interactive's flower model, just to give you a visual to think about the different ways in which there are co-benefits. So down here, the red petal here of the flower is health and well-being and safety. And so that's basically improving mental, physical, and spiritual well-being and creating safe conditions to work within. The next one, jobs and assets, providing a meaningful work at a living wage and building assets in the community. Water and food and water is increasing access to healthy food and clean water. So how does a solution contribute to that co-benefit? Resilience over here is in building people's capacity to survive even when you have significant disruptions. We've certainly had significant disruptions this year with COVID. Climate change will produce a lot more longer reaching issues that society has to be able to be resilient towards. The next one is energy industry and mobility. Bringing people secure access to energy and the ability to make things that they need and the ability to get around. And then the last one is connections, is leaving people more connected to each other and opening new opportunities for multi-solving. So the second document in that Google folder is basically using the same framework of the different solutions. Here's energy supply, transportation, building and industry and growth, land and industry emissions and carbon removal, and giving examples of what are the co-benefits for implementing solutions for these. So for example, coal, taxing coal reduces air and water pollution, improving community and ecosystem health. So it's one example of the co-benefits that have a much more immediate impact while you're trying to address the issues of climate change. And then the other is the equity considerations for for each solution also. So for example, we'll just look at coal again. Taxing raises energy costs, and low-income individuals that rely on coal jobs and coal for energy suffer the most with these negative impacts on the production of coal. So those are the kind of equity considerations I will ask you to think about. So now we're actually going to get to using the model. So I want you to think about what actions that you've been involved in implementing, or either individually or your community or the organization that you work for. What are those different kinds of solutions that you have been implementing or know of being implemented? And think about them being implemented on a global scale. Let's say everyone in the world actually implements that solution, because EnRoads is a global model. So you have to think about it in that action, in that context. So I want you to think about that and then type your thoughts in the chat, and then we'll be demonstrating exactly how EnRoads works. Oh, I see. I made a mistake here. I went back to the chat and I realized it didn't get sent to everybody. So I'm going to put that into the chat now. There we go. All right, does everybody have it? Hopefully everybody has it now. So if you can now put into the chat solutions that we should try. What are the kinds of things that, and actually if we have, how many people do we have? Diane, can you tell me how many people we have here? Okay, we have 13 people. So actually,
9 participants and us.
Okay, So since we have so few people, you don't even have to put in the chat. You can just unmute yourself and offer particular solutions. I wanted to, let's just try some out and see how they work. Anybody want to?
Blue? Can I be heard?
Yes, Lawrence,
Yes.
go ahead.
The degradation of the Earth's climate is falling so rapidly. I think the fastest way to arrive at a solution, and it's not going to be easy, is to bring the industry of producers and offenders together with groups like this and perhaps other universities, and to have a summit. And
Okay, so but at the summit, what do you think that they should decide to do? That's what we're going to test out here.
well,
Let's say we have that summit.
well, the first thing is to get the producers to be willing to attend the summit at the very highest level. That means at the CEO level, and with advisors, of course. And that has to be acknowledging that there's an urgent problem that has to be addressed now. And the solution is for those companies that are making money on being problems, and it needs government assistance, I'm sure, to, in a very short period of time, come up with ways to make as much money or more doing things that help the environment and reverse global warming, not
but what
contributing
would you
to
think?
it.
Yes, I agree that that's a challenge to get them to come to that summit. But once they're at that summit, which of these solutions would you want them to try?
It's not to pick one solution right now.
But it is. That's what
No.
our job is.
I agree with that, but the objective is to get these companies participating in the process to find and implement the solutions. So
Tamara, maybe I can jump in here.
I will be
Lawrence,
part of the game.
Lawrence, I think you're in the wrong workshop if you want to go down that path. When you go through the EnRoads workshop, you can address those types of things. In this workshop, we're simply trying to understand what the levers are. So for this workshop, what we're doing is understanding how policies impact outcomes. That's it.
I have a suggestion here.
Go ahead, Tina.
Yeah, I'm Tina Dreimann, founder of Better Ventures. We invest in startups that solve our problems. But as my grandmother was a tree hugger and we face massive deforestations on a yearly basis, I would go for the trees, but both. Firstly, stop deforestation and go into afforestation because those are the most important emission binders.
Okay, so
in addition to that,
let's just try that one. I'll give you the floor back, and you can say what you want to do in addition. But let's just try these one at a time.
Yeah,
let's try deforestation here. Now we've highly reduced deforestation, and we've gotten this temperature down from 3.6 to 3.5. And you have the model here has, we can replay the change, and let's look at its impact on the global sources of primary energy. And there's none. There's no impact here because you're simply taking you're taking carbon dioxide out of the atmosphere, but you're not affecting the energy.
You're not stopping it. That makes sense.
And then let's go to afforestation, and we've gotten this down another 1/10 from 3.5 to 3.4. So here's the net greenhouse gas emissions. Notice that it really doesn't diverge from the baseline until we get past 2040. And again, if we look at the impact here, we're taking carbon dioxide out of the atmosphere, but we're not impacting the energy supply. Okay, so now that we've looked at those two, Tina, what is the other ones that you might want to implement?
I mean, as you mentioned that the biggest driver for the emissions is currently coal, wasn't it?
Coal, all right.
Yeah.
So what would you like to do?
What happens if you stop the, I mean, if we all change to new zero, I mean, that would be the best way to do it, but it's not there yet, right?
Well, the thing is that you can implement new zero, but that doesn't get rid of coal. And so I
Only if
think
you
one of the things that
substitute.
I'm hoping that you'll see here is it's multiple solutions. It's not all going to one solution. So let's try one. Suggest one to try first. We can try them all, but let's suggest one to try first.
Let's get rid of coal.
All right, so we're going to tax coal. It's not real. Is it realistic to say we're going to get rid of coal? Probably not. We're going to highly tax coal. We got this down to 3.3. Let's replay the change and let's look at how this changes again. And you can see that coal goes down. And I'm going to actually change this graph a bit so that we can see something else. So this is the same graph, but instead of those stacked wedges, these are just the lines. So here's coal. The brown line is coal, and the red line is oil, and the blue line is natural gas, and the green line is renewables. And watch what happens as I replay that change. Coal goes down a lot, but then natural gas and oil and renewables all go up. So basically, by taxing coal, people use less coal, but then they move to oil and natural gas as well as renewables. And so you're still increasing the amount of greenhouse gases in the atmosphere to some extent. So do you want to try a different one? Does somebody else want to offer a solution to test out?
Yeah, I would go for the buildings.
Buildings and industry. And what energy efficiency or electrification?
Energy efficiency.
Okay, so let's increase the energy efficiency of buildings. So that got us 0.2 of a degree. And so you can see these net greenhouse gas emissions now are getting pretty close to being flat from what they are now, which is a good thing in one sense, but remember that that means you're still emitting that much more gas in the atmosphere. The gas in the atmosphere is continuing to go up, even though the amount we put in each year is constant. But we've now gotten down this to 3.1, and let's look at this here, and I'm going to replay this change. And you can see that all of these go down, and by increasing energy efficiency, you reduce the demand for energy. So that's why the global sources of energy go down. But also notice, I'm going to replay this again, that most of those changes occur after 2060. There's not a whole lot of impact by 2050. And so there's a transition here of things happening. But in this early phase, there's really not a whole lot of changes. All right, so I'm going to go a little bit deeper now. Tina, I think it was you who suggested we get rid of coal. So this is the high level of the model, but we have these, each of these solutions has 3 dots on the right-hand side. And if we click on those 3 dots, we get a whole lot more information and control. And so this is, this first one here is the same as that lever we just pulled. And when we say we highly tax it, we are taxing it at $49 per ton of carbon equivalents. If you want to learn a little bit more about it, you can, about what this actually means, you can go here. But then you have options for a whole lot of other things. You can change the year that the taxes start and stop. You can just say that you're going to reduce the utilization of coal. So Tina, this is one possible avenue in which we can just present reduction of coal. So let's just put a number in here. Let's say reduce coal by 20% and see how much of an impact it has. Look, notice here we are at 3.1. Where's my mouse? Oh, there it is, 3.1. And now we're going to implement this. See, it actually didn't have, reducing the use of coal by 20% doesn't have too much impact on the temperature. If we replay again, this is the coal primary energy demand. So that's the same as this brown line here. If we replay that, you can see that by reducing the utilization of coal, we do decrease it some. Another thing that we have control of here is stop building new coal infrastructure. And this is a key issue. So when companies have a coal plant, that is an investment, that's an asset that they don't want to abandon. Coal plants, their lifetime is on the order of 30 years. So those plants if you stop building new coal infrastructure, then over a period of 30 years, that will impact things. So let's just give that a try. We're going to stop building new coal infrastructure in the year 2025. And you can see that already had a 0.2 degree change. And you can see now by 2060, you have significantly reduced the amount of coal. And let's see, did the others go up? The others into the natural gas went up, renewable energy went up, the oil didn't change very much at all. So that's another way that you can control this. You can also accelerate plant retirement. So how much are you going to change when those older plants get retired? The other information that's available here, if you click this little eye, this gets you examples of the different policies that might influence coal. The big messages, key dynamics, but the key piece I wanted to point out to you is the potential co-benefits of discouraging coal. Reducing air pollution from burning fossil fuels, produces air quality and health outcomes, and less coal mining reduces metal discharge and waste from the mine sites. There's also those equity considerations here. So these kinds of issues need to be considered when those entities that you work really hard to convince to come together for a summit need to decide. These are the kinds of decisions that they have to make in order to implement solutions that are effective. Okay, does anybody, so we're working towards getting down to 2.9 to 2.0. We're only at 2.9 now. Are there any other suggestions for
What about capping all gas fields?
capping all gas fields? Let's go under here and see where that might be. So we can reduce the utilization of gas. You want to do that by 100%?
No. There's methane that's just being, spit out into the environment. By capping it, you don't have any of that loss.
Okay, so let's go to methane. All right, we'll go to methane here. And methane you have here under, this is methane in general. If you pulled the lever, this is what you would implement. But we can go to the detailed settings, and you want to energy and industry emissions. And so we want to reduce those. So I don't know, let's see, you want to do that by 100%?
Yes.
There we go. And it got us down only to 2.7, from 2.9 to 2.7. So these are the non-greenhouse gas emissions. And you can see that that is, again, it doesn't really diverge from the business as usual until about 2030. And then let's look at another set of impacts here. Now that we've gotten a bunch of solutions implemented, we can look at other impacts. And so we can look at the temperature change. So here's how temperature has changed with respect to that baseline. Now that we have some solutions in, there's the current scenario. We're down to 2.7, and for guidance, this is 2.0, and this dotted line is 1.5. Let's look at one that is interesting. Well, let's look at air pollution from energy. So this isn't actually a climate variable, it is an air quality variable. The particulate matter that's 2.5 microns or smaller. This has been judged to be, that is the threshold for the United States Environmental Protection Agency to control particulate emissions. And you can see that that has an immediate impact and goes down well below what it was even in the year 2000. So this is a significant impact here. That is a co-benefit. And then one other that I want to look at is sea level rise. So this is interesting here in that the sea level rise at 2100, it is projected to be 1.15 meters higher than it is today. But with this set of solutions, it's only 1.05 meters higher than today. So the impact is not the change of the impact of all of these solutions doesn't change sea level rise by all that much, and it doesn't even really diverge from the baseline until about the year 2070. So a lot of what we've put into the atmosphere already is already going to impact sea level and cities on the coast. So Stefan has, go ahead, Stefan.
I'd be very interested in the impact of the electrification of transport.
Okay, let's give that a try. Let's just pull the lever first, and you can see here that, let me go back. Oh, wait, I'll do it this way. Let's see. Okay, back to that one. What was that CO2 emissions? So we did the we incentivized the electrification of transport. Let's see if there are other options here besides. Now, what this meant, incentivizing it meant increasing it by 47%. And what does that actually mean?
So this is probably government subsidies for the purchase of cars or charging infrastructure.
All right, so policy mandate for new land transportation to be powered by electricity rather than fossil fuels. Land transport globally reflects about 85% of transport capital. So is this number a number that is one that you would think of implementing, or would you want to implement?
Does it mean the fleet, the percentage of the fleet that is electric? Is that what it means? The 47%?
Yeah, so this says increased purchases of new electric cars and trucks and possibly even ships. So this is increasing all of those.
New, okay, no, I think we can go up to 100% realistically. The purchase, new vehicles, there will be only electric vehicles in 10 years from now.
Stefan, just a little comment from my side, Wolfgang here. Think of it, this is on a global scale. So of course you will have markets like Africa,
Fair
South
enough.
America, etc., which are far behind, just as a reality check.
Very true.
Right. So maybe we should make this 50%.
Okay. That's not much, huh?
No, it's not. It got it down to 2.6.
Okay.
And so electric share of total capital transport this is a percent. And so it sort of flattens out at about 40%.
Mm. Tamara,
Okay,
one question.
Yeah.
How did you model in the change in our population's diet? I've read that this is a big lever. For
All right.
example,
So yeah. So here, if we go to this one, it says it basically comes here under agriculture.
Okay.
So if we change the agriculture, people go to vegetarian diets, you reduce the amount of methane production from agriculture. So we can pull this lever. How much? So I would say let's just try 50% here and see. Oops. Let's try 50% here and see what it gets us. So it gets us another 1/10 of a degree. Still not there yet. One of the things I've noticed is people you're not really addressing any of these here. These are the emissions we're having now, and you can see that oil and natural gas are still producing a lot of energy and thus emissions. So this is net CO2 emissions. And you can see that it's pretty much, we're still producing it even all the way out to 2100. So what we want to do is get this line down, and let's see if it's all energy. Here's all of the greenhouse gas emissions.
And if you increase renewables or new zero carbon, will the others go down? Or
let's see, renewables, which others go down? What would you think would happen if you increase renewables? I
would hope that, for example, coal and oil are substituted. But
okay, so first of all, with the solutions we've implemented so far, coal is next to zero after 2060. So we really need to get at oil and natural gas, but let's increase renewables and see how that impacts the red line and the blue line, oil and natural gas. You can see it doesn't impact it all that much. They're still there. But let's see if we go to oil and let's just try to stop building new oil infrastructure. Now look at what's happened here. Is that this red line took a nosedive. And you can see how it takes some time. It takes out to the year, about 2045. But renewables goes up, but natural gas is still pretty much up there.
I mean, do you know if the model actually considers the fact that the consumption of power will increase? Or is it is the consumption constant, or is a variable?
No, the consumption is a function of a lot of things. One thing I know it's a function of is demand. So
yeah, of course.
Demand is controlled by population. The more population we have, the more we need energy to grow food.
Yeah, but there are other factors as well. I mean, for example, digitalization means many things we run on computer, and the most powerful computers, they need water to cool down. So it's a huge power consumption as well.
Right. Yeah. So
if the population goes down, I mean, if the population goes down, you can assume that automation will be much higher.
Tomorrow I got on late. It's Claude, but you didn't do anything with a carbon price?
Nobody has suggested that yet. Would you like to suggest that, Claude?
Yes.
Okay. So one of the things, we've addressed coal here and we've addressed oil, but another way of getting at all of the carbon intensive fossil fuels is a carbon price, because it impacts coal, oil, and natural gas. And it impacts coal the most because it's the most carbon intensive, and oil the next, it's the next most carbon intensive, and natural gas the least. But in this scenario, we've already impacted coal and oil tremendously. So let's put a carbon price.
I'll walk later, Denise. Sorry, I was talking to my assistant.
So you can see we've impacted a high carbon price, and that has impacted the natural gas here, but it has not sent it down to zero. It's and so notice here that in this scenario, the renewables goes up and bioenergy goes up. So because you don't have these other sources of energy, it gets translated to people using these to using renewables and bioenergy and nuclear energy. There's a low level of nuclear energy. We've not subsidized that here at all, but carbon price does have an impact on all three of these. And that actually did get us to 2.0 degrees C. So we actually achieved the goal, but one of the things to notice is that there wasn't any one solution, that there need to be an entire suite of solutions. The other point is that we have the model, and in the context of using the model, are making the assumption that everybody around the world implements all of these solutions at the same level. We know that that is not realistic. And in fact, some solutions are easier and more effective in some locations than in other locations. So it would probably take a suite of more of these solutions in order to actually achieve this goal.
Tomorrow, well,
Yeah.
what happened to price of energy, cost of energy for people using this scenario?
Okay, let's look at that. Oops. So actually that's interesting. And this is where you have to make those equity considerations. In this first, what is it, 30 years, the cost of energy for people goes up tremendously. and then starts to come down and goes below the baseline scenario. So a lot of consideration has to be, if you're going to put this carbon price on a tax coal, you need to figure out how it is that you're going to use that money to help those that really don't have access to those kinds of funds to be able to use the energy that they need to support their lives.
Tamara, can I ask a question? This is
Sure.
Bertram from Systemic. If we want to hold countries to their 1.5 Paris climate obligation, would it be possible to peg the EnRoads model at 1.5 degrees or 2.0 degrees and essentially say, well, you as a given nation, you can change any of these variables, but the model will compensate for your choices with all the other choices to always ensure that you stay within the 1.5 to 2.0 corridor. So for example, if a country says, okay, we don't want carbon prices because we don't believe in that, then the tool would say, well, fine, but then you have to, put a price on coal, oil, natural gas, and so on. And if you don't want that,
there's not a way to do that automatically, but we can ourselves say, we are not going to price carbon. We're going to make this zero. So now we have the ability to go and try what all the other solutions we need, because there are other scenarios that will get us there. So let's say we tax natural gas and we have a new breakthrough in carbon, and we technologically remove this from there. So now we've gotten out, so that the model doesn't automatically do it, but you have the opportunity to explore which other solutions might be effective without pricing carbon explicitly, although we've already taxed coal because that was suggested earlier.
And can I ask a follow-up question, Tamara? I don't know how concrete models from the IEA or other international organizations are. Is there a way to essentially easily feed them into the EnRoads model to validate that suggestions that come out of these associations of fora are actually impactful enough to get us within that corridor? Or is
you
there
can
any
take the outputs of those models in terms of what they suggest in terms of solutions and implement them. You can't just feed it in. You have to sort of use your own mind to determine, all right, and this is what we have legislators do when they're considering different kinds of legislations that may impact, whether it's a carbon tax or whether it's laws about energy efficiency or electrification, whatever it might be. They can go into the EnRoads model and test these solutions and see which ones have the most impact. This is what's called a systems dynamics model. What that means is that every solution you implement impacts a lot of other things. And so we've implemented a lot of solutions here, but I would suggest to you that if we made this go back to the original format and we tried each of these solutions individually without building on them, that the sum of those would add up to more than this 1.9 degrees C increase here. But the solutions aren't additive. Once we tax coal, and then if we added a carbon price, if you're already taxing coal, adding a carbon price won't impact it a whole lot to the same extent as putting the carbon price on without taxing coal explicitly. So this is a tool for legislators that legislators can use to say, okay, which of these different solutions should I back the most? Which one is going to have the biggest bang for the buck in terms of my community, and whatever their constituency is. Keeping in mind again that this is a global model, and it does make the assumption that the solution is implemented around the world. Did that answer your question?
Yeah, thank you.
Tamara, if I may, so when we have a model like this and we're looking at reducing various variables, that probably has very much to do with the current level of distribution across the globe. Is there a model of changing societies and changing economies included in this, so that, let's say, China's progress, maybe India's progress, India using up, I think, 0.76 Earths every year, US somewhere around 7 Earths, Europe, I think 5 Earths, something like that. Is there an economic shift inside that as well, to see what the impact is, or how is that actually modeled into this?
So the economics is included, but it's not one of the solutions you can implement. One of the things you can do, though, is on this population and GDP, and I'm not as familiar with it. So let me see. Right, so these are different researchers who have come up with those kinds of economic models of the impact of those temperature changes on the GDP. And what you can do in the model is that you can pick one of these and then look at the impact of those on the then look at the impact on the GDP. But other than that, this is not implementing a solution. This is using models of what various researchers have said, that in using their own economic models, an increase of this amount of temperature will have. So this, for example, Dietz and Stern have said that a temperature change of let's say, we'll say 3.6 degrees will have a reduction in GDP of on the order of 35%. That's research that's independent of the EnRoads model, but it's provided here so that you can see what that is. But you can't implement that because none of these are just different social scientists coming up with their own models. Dietz and Stern happen to be the ones that it looks like that has the most impact. If you have an increase of 5 degrees C, which we're not headed there, at least, and this is only by the year 2100. A lot of these temperatures will continue to increase after that, but this seems to be the one that's the most sensitive. Burke is somewhat less sensitive, and so all of these are impacts on the GDP ranging from about 5% to on the order of 20%. So that's how you can look at it. And the other thing that I wanted to point out, I mentioned earlier, these are the assumptions in the model. And you can go to any of these and change them. If you don't believe that the climate sensitivity is 3.0, and each of these little arrows will tell you what it actually means. And I won't go into this here, but it tells you the source. So the model is very transparent in terms of what the assumptions are and giving you the ability to change them. So usually for climate sensitivity in the climate modeling world, which was the first part of my career, I did climate modeling, is if you double the carbon dioxide, what is the equilibrium temperature change? And if you do, so that's saying is the climate really sensitive to the amount of carbon dioxide, or is it not so sensitive? If it's not so sensitive, then that sensitivity number will be, for a doubling of carbon dioxide, this number might be smaller. If it's more sensitive, then this number will be bigger, and you have the ability here to change that. And so there's lots of other different kinds of assumptions that you can impact, and you can look at what each one of these means, what this value actually is. And you can go to their online guide and get the actual resources, or we can email them. If there's a specific question, we can email Climate Interactive and get further information about how it's actually implemented. So this is where the assumptions are input.
Question regarding region, what does that actually cover? Do you cover cities versus suburbia versus rural in terms of carbon consumption per capita?
No, this is all global.
Right, but globally, do you have any picture of what carbon consumption per capita is in highly urbanized areas versus rural?
Climate Interactive may, but I don't. I can ask that question. I'm sure they probably have that for countries, but I don't know about urban versus rural.
For instance, if population shifts to urban and urban is more efficient, that may be a positive impact.
It could be. It could be. It's not something you can implement here directly.
Mm-hmm.
Let me just go back to this. Okay, so we just have a few more minutes here. And so I'm going to just go back to the slides to finish up. We did get to let's see. Okay, so I'm just gonna basically this overview is that there are a lot of these solutions are possible, but implementing at the global scale is a challenge. But there are companies that are starting to take action. That's clothing brand H&M has promised to double its energy efficiency by 2030. Over 260 of the world's largest companies have committed to using 100% renewable energy. But using renewable energy by itself isn't going to get us there. We really have to address keeping the fossil fuels in the ground. And Microsoft has pledged to be carbon negative by 2030. And what that means is removing more carbon from the atmosphere than it emits.
Also, Tamara,
yeah.
When they talk about that and they're switching to renewables, do they include the emissions in China required to build their solar panels, things like that?
I can't answer that directly. I don't know that that's a specific variable, but they do take into account whatever is. They do take into account the larger picture that is reflected in the in those aggregate, more complex models that integrate the physical system with the economic system and the social system. But I don't know that they actually have that kind of a variable. First of all, I think it's that's probably on the sort of finer side in terms of what can be integrated explicitly in the model.
Yeah, no, I'm just saying when these companies say they're going to 80% renewable, they most of them, I'm told, leave out their supply chain.
Yeah, that is a big issue. And more companies, at least I know in the United States, look at their supply chain as well as their own manufacturing. So it is a very good question as to whether they consider what's being what has to go into, what kind of emissions go into creating those solar panels if they're made in China. I don't know that. That's a good question.
What is the carbon imprint of Bitcoin and its ilk today, and what is it feared to be in a couple of years?
I don't know. Okay, so so we actually only have a couple more minutes. I'm just going to go to this last slide, and it's another point that I want to make was we looked at the outcomes were that it takes a lot of different solutions. There's not going to be one solution, but we also have to build the political will, and not just in our own location, but globally. So this is a diagram that comes from Climate Interactive, where you look at the personal level, and our individual actions aren't going to have a huge impact, except in the way that they influence others. So if we begin to conduct these actions and influence our families and our communities and our companies, we will get out to these having a larger impact at the social level, the organizational level, and the public level. And ultimately, we need to impact culture as a whole. And culture from one country to another is also really, really complex and difficult. But it's only through this chain of influencing others, as well as and as well as demonstrating and conducting those actions on your own, that that we will have an impact. And so thank you very much. And if you have other questions, you can email me or you can visit Climate Interactive. I actually never got to the point of sending you the, because we didn't go into breakout rooms, I never sent you the link. I'm going to, I wanted to just get this here. So one of the things you can do is I'm going to put this link in, you can copy the scenario link in of the model in the state that it is now. So if you were to implement this in, if you were to do this workshop for another group of people, and I'm happy to talk to somebody if you're interested in doing that, this is the link to the scenario as it is now. But you can also get to the model itself in the base form. Here is the EnRoads site, and you get to this site by going to, I'm going to put this. So I put the email, the URL that you need to get to this site, and then this is the EnRoads simulator. So this is bringing it up again new. And so you have the model in the original state. So you now have the links to get to both of these versions. In terms of using it in schools, there are also student assignments that you can have your students do. I actually run this workshop with my class, as well as Claude mentioned and Tim mentioned the C-ROADS model. That's that negotiation model in terms of world governments. And you can, I run that in my class also. So they actually run well in a pair, because when you using the C-ROADS model, the decisions that the nations or nation blocks have to make is, when is my nation going to stop increasing its greenhouse gas emissions? When are we going to start decreasing them, and at what rate we need to decrease them? And when I ran that with my class, and then they said, well, how can I make this decision for India when I have so little information, and how are we going to start decreasing emissions? And then that led right into the C-ROADS model, where we got to test different kinds of solutions out. So it's a very good tool to use in education also.
Tamara, thank you so much for taking us through this. And I think, I don't know if it was an advantage that we didn't have the breakout rooms, because we could listen to you and actually follow this module, the modeling live as we were speaking. Frankly, if I may just try to find a few words, not that I need to repeat what you said, but what it did leave me with is just being flabbergasted at the amount of levers that need to be activated. The tool itself, I think its complexity is something that I only discovered now. We've seen this tool before as a cockpit, but the cockpit says very little unless you actually go into the other levels and then discover how complex this tool actually is. So I hope others would agree that they might find some interesting insights by using this tool. So thank you so much for that. I think, frankly, one thing that really did impress me is I have a very good friend from old times, and we're just preparing an event with him. And I had a discussion about, how much impact on, let's say, temperature reduction did COVID actually have? And he said very, very little.
Yeah, that doesn't surprise me. It looks like Wolf froze.
Froze on mine too, Tamara.
Yeah. There's nothing I can do to help him.
Let's give him a minute.
And there was an impact on the amount of emissions, but first of all, I don't know that the impact on emissions of COVID was really very large, but also there is, as long as emissions continue to go up or even stay constant, it means that we're still putting more greenhouse gases in the atmosphere. So it would have really very, very little impact on temperatures long run. Hello, Wolf. We see you came back.
I was lost just now. I don't know who turned me off. It was my network, so I'm now connected to my mobile phone. I'm so sorry. I don't know where I was lost, but just to make it short and not overstretch time because we're actually at our limits. One thing that did frustrate me talking to my friend was that all the measures that we experienced during COVID now, with the reduction of traffic, with reduction of air movement, would not even suffice remotely in reducing the temperature change that we're facing. So looking at the model and looking at how many other levers would need to be activated, from reforestation to various carbon taxes, that complexity I find is astounding. And in particular, putting a lever down is one thing, but actually thinking about the policy implications, how many lobbies will be going up in arms against any changes, right. How many strong politicians we need to push things through. Each one of those levers will have so much complexity, and not just in one country, but even more so when you think about the industrial world having to play the most active part in it. So I think this model on the one side intrigued me, on the other side just underlined the daunting task that we will have. And it, as you mentioned yourself, it's very much about the political will. So this is also, if I may quickly share my screen again and finish off. The political will is one of the things that, frankly, we will want to look at in more detail by engaging in new events. Now, one good thing, Tamara, is that you helped us provide you with a little certificate, which we thought is better than actually sending you a bottle of wine. Better is, of course, relative. Maybe you would prefer the bottle of wine, but instead we actually give you, or we've put money into buying you 5 tons of CO2 offset. So hopefully you will be able to enjoy that. We will send you this certificate in the next few weeks. So at least that hopefully will be a good little gesture of giving you that.
Thank you so much.
And in fact,
I appreciate that.
and Peter, who unfortunately isn't here right now, has done the calculation. So we produce about 300 grams of CO2 for this event, but we offset it with 5 million grams. So at least this event is definitely CO2 negative, which is quite positive. So hopefully that'll do just one little extra gesture. If I may end today's session. So obviously all of this wouldn't come together without the support of different partners, many partners, obviously many of them connected to MIT. And first and foremost, I would like to thank Diane from the Alumni Association for providing us with all the technical support and the backbone to make this happen. I've seen that a number of people who've participated happily, I've seen that are not necessarily MIT people, but have been to Harvard or Wharton or Cambridge and other places that surely will have their own culture of discussing and thinking about these topics. So a warm welcome that you did join us, and we're very happy if this doesn't stop at MIT but goes on beyond that. So that is great news. Maybe for the Alumni Association and probably anyone who's interested, because these online events, of course, are pretty open. We are planning now the climate policy, which is exactly this political will issue, where we will be discussing what the political mechanisms are actually of making some of those hard measures work. In countries, in world governance, but also, of course, questioning whether democracy will actually be a challenge, making hard decisions moving forward, and whether other systems might actually make it easier. Then, for the MIT Club members, we have our annual general meeting planned for Stuttgart, just to let you know, from the 17th to the 9th of September. Corona pending, of course, as always. So we're going to be monitoring the situation to see how things pan out with Delta and anything else. Then for October, we're looking at a sustainable manufacturing panel discussion, which we will obviously let you know in time. And then, as Helmut was pointing out, we have our big event Schule mit Wissenschaft in Bremen this year on the 12th to the 14th of November. Also a hybrid, just like the AGM, so in presence, but also as a hybrid. So we will be streaming some of it. And that this is really with a target group towards teachers, getting STEM teachers excited about some of those challenges and some of the opportunities, often with extremely good speakers. It's quite common that we have a Nobel Prize winning speaker for each event every year. And then we'll probably end the year with some Christmas get together, again, Corona pending. So this is just a little outlook of what is happening. But that said, frankly, it is up to me now to just thank you so much, Tamara, for taking us through this, for helping us understand, and actually also giving us access to a really good tool that we can use to model each person in their own field, what impact maybe our actions can have, and how we can understand the complexity. So thank you very much. And for all the participants who've taken the time, we really greatly appreciate it, asking questions. And if you have any more questions, either, if Tamara, if that's okay, contact Tamara directly, or just let us know if there's anything that we can
put my email in the chat. So if anybody wants to.
Great. Lovely. And I think I wish everyone a lovely rest of the day here in Europe. It is now time to open a bottle of wine and enjoy a wet and rainy summer, at least in Germany, which when we look out the window, we always say it's good for nature. Thank you.
Thank you very much.
Thank you. Bye-bye. Bye.